The next thing I want to draw your attention to is another big feature of computational multiphysics, which is the ability to bring in information about the different types of physics that you're solving into your material properties, which are then used to solve those physics. So coming back to the chicken patties tutorial, if you go under components and you take a look at the two types of physics that you're solving for moisture content, which is diffusion of humidity, of moisture. Sometimes it's a good idea to go down to this tab, the dependent variables, and just double check that you do have the correct variable name. So C is the concentration. Note also that the units that are associated with that. The reason why I say that is sometimes if you have multiple geometries, COMSOL likes to index them by adding on a 2 or a 3 onto the end of it, and it's just useful to have sometimes. Okay, if you go to the heat transfer in solids, right, we're going to find that the dependent variable there is temperature, and that's in kelvins. So we have concentration and we have temperature. Now, when we go to define our material properties, those are up here under the definitions in variables. And if you expand this over here a little bit, you're going to see, lo and behold, our dependent variables. Concentration here, temperature is actually buried into dT, and then that's featured here. So what that means, this is thermal conductivity, this is a temperature difference, and then heat capacity. So what it means is that the heat transport equation is being influenced by the heat capacity, which is temperature dependent, and the thermal conductivity, which is both temperature and moisture dependent. And as this is being solved, it's being solved self-consistently. You'll also notice that the units are being worked out. This is why you want to use all the correct units when you're defining your parameters way up here, because then when you go to define compound expressions, you can actually make sure through dimensional analysis that you've got the correct result. The other thing to note here is that this definition, so that the temperature variable, dependent variable, and humidity dependent variable exist within the component scope, and so does the variables definition. So if you tried to define these equations up here in the global scope, it's not going to be able to because it won't know what you're talking about. What this is actually doing under the hood is it's making the differential equation nonlinear because you have a property that depends on the solution multiplied by a differential of that solution. What you're going to learn if you haven't already in numerical methods is how you solve those nonlinear equations. Generally speaking, it's through something called Newton's method, but there are other techniques too. And the idea is that you have to use gradient information, which is derivatives, in order to find your solution, and you iterate down onto your root. What COMSOL provides nicely and doesn't really make a big deal out of it is a very powerful symbolic logic engine. So all of these expressions in here, you're able to take the derivatives of it and move them around, and COMSOL actually has that very nicely built into the engine. So when you make it a nonlinear differential equation, you actually don't really notice very much, which is very useful.